astrophysicist at Siena College, right?
Yeah.
All right. 3, 2, 1. John Moustakas, astrophysicist at Siena College. These are my favorite topics in the world. I told you on the way over here, this is super exciting for me. I'm fascinated to talk about this stuff. So thank you very, very much for coming here today.
You're very welcome.
First question, where does all of this come from?
Define all of this. So
why are we here and where did this come from, man?
It's a great question. And I think if we knew the answer to that, I'd be out of a job to some degree. And so science, astronomy, physics, all of that is sort of the pursuit of trying to understand, the why and the how and the where, both where we came from, how that happened, where we are today, understand the world around us, and then what our future holds. So I cannot answer it, but it's a big part of what drives me to science, because we're always asking questions, we're always trying to understand new phenomena, new ideas, and I love the fact that in science, science evolves. Maybe we'll talk about evolution, but science really does evolve. It's not like this sequential process, unlike, where you go and you pick up a book and it's like, oh, I got to study, I got to memorize all these things. That's a big part of research, that we don't have the answers in the back of a book. And so we ask a question, we make observations, we collect data, and we see where the world takes us. And then the next day we're asking a different question, and we've thrown out our old ideas. So
that's the story of people, right? Evolution.
Yeah.
It's the story of incremental improvement, incremental knowledge. And we're always waiting for the next person to be born to figure something out, right? Be like, hey, man, we figured all this out.
Yeah.
Now what?
Right.
And that's where you are.
Well,
you're in the now what.
Well, yeah, one hopes, but there's a joke that comes up a lot, a joke among people I hang out with, maybe. But when something really awesome happens or has developed, or a new idea or new discovery, we say, well, why have we been working in this area or on these questions? We should have just waited 30 years for that person to make that discovery. And so you could say that right now, like someone will figure out, self-driving cars, or, the nature of the universe, or whatever. We could just stop working. But it really is like everyone has something to contribute, right? So we have had these sort of threshold moments, people, Einstein and Newton, all these giants, and those are the people we read about. But they're a lot of time, their ideas are revolutionary because they really are thinking outside of the box. I don't mean to minimize that, but everyone has a part to play. Everyone makes contributions in small and a lot of times unrecognized ways. And so, the literature of when we do a study, say we want to ask a question, take some data, we write it up, like that one paper might not be, and almost always is not revolutionary, right? Like it's incremental, but that goes into the body of knowledge, right? And so you're right that it may take the right person and a person to synthesize all of that. But I think the key really is incremental, that science is incremental. Sometimes in the wrong direction, most of the time in the wrong direction, but that's kind of how it works.
But you can say that with a smile, because it's fun to see going in that, oh, we were wrong. Like that's the thing that it takes a type of personality to be a scientist, to be like, okay, this might be a complete waste of time. It might be.
Yeah.
Like, so let me rephrase my question differently here.
Okay.
So as of right now, 2018, your perspective, what's our best guess of where all this came from?
So we have a basic understanding. We think we have a basic understanding of the universe, and I'm assuming you're talking super big picture here, right? Not like the formation of the Earth, but like the formation of like the cosmos.
Any way you want to interpret that question,
yeah.
It's open.
Yeah. Okay. Well, so I mean, I can tell you a quick story of what we think. Of how we think things have evolved and changed and come about. But, anyway, so let's get to the big questions after that. So we have measured the age of the universe to pretty good precision. So age of the universe is about 14 billion years. So the Earth is about 4.5 billion years. The Sun's about 5 billion years. So basically the solar system's been around for about a third of the age of the universe. But we've measured the age of the universe pretty precisely. And so that the inference there is that there was a beginning, right? Like, because for something to have aged, it needs to have started. We have inferred the beginning of the universe, which we call the Big Bang, but really that was actually coined by an astronomer named Fred Hoyle, and he coined it in a derogatory way because he would, that's ridiculous that the universe started in an instant, some kind of a Big Bang, and somehow that caught on, and that's what we refer to it. So just like with a bomb exploding, right, the fragments are moving away from that very instant of when the explosion happened. So we can measure that movement away or that expansion of the universe today, and we've measured it very precisely. So basically the idea is when we look at galaxies near and far, they're all moving away from us. And so that implies that if you, just like a movie of something exploding, if you kind of turn that movie backward, play it backward in time, everything must have come together to a singular point back in time. So that time was, like I said, 14 billion years. So within this, expanding universe, gravity reigns supreme. So gravity is what keeps us bolted to the Earth, and the Earth, it's what gives the Earth its shape, and the Earth orbiting the sun, and the sun orbiting the center of the galaxy, and galaxies pulling and tugging on each other. And so even though this whole universe is expanding, space-time itself, locally in smaller regions, you can have gravity pull in gas. Most of the normal matter in the universe is hydrogen gas, the simplest element in the universe. Second most common is helium. So about 99% of all of the matter in the universe is hydrogen and helium. It's not, carbon, nitrogen, oxygen, the things that we know and love and need to survive. So that gas can get pulled in, and once it gets dense enough and hot enough, you can start making stars. From stars, you make galaxies. So at one point, there was, in our part of the universe, that gas started collapsing and the Milky Way started forming. And the sun was born out of that process of stars forming from new gas clouds, and around those the Earth was formed and the other planets, and then on that that primordial soup, right, life arose. And so here we are in Troy.
You're gonna see me grinning and smiling a lot while you're talking, because this stuff it's exciting. It's very, very exciting. Yeah. And I can tell you also have that excitement. Yeah. I don't know how anybody's not excited by this. It like, come on, listen to that. Like, the things you mentioned about how everything, just the gas coalescing and all this forming and all this, and gravity is everything, right? Without gravity, none of this works. But how much do we know about gravity?
So our theory of gravity comes from Einstein. It's called the general theory of relativity. So a theory, when a scientist has a theory, they mean something very specific, right? So colloquially, you and I might say, I have a theory, sort of an idea. Maybe it's right or wrong. Who knows? That's my theory. That's what I think happens, right? So scientifically, a theory is, a set of ideas or an idea that both explains things you observe and makes predictions. So you say, okay, well, the theory of gravity predicts that X should happen before those observations have been made, right? So you go off, you measure X, and see how the data, how experiment compares to your theory. If it's right, then it's like, woohoo, fantastic, right? If it's wrong, then either your theory is wrong and you need to adjust it, or maybe there was some some other part of it that you could have changed, or you just, if that happens repeatedly, then you got to abandon ship. So very famously, right? So Einstein's theory of relativity came out in about 1915, and one of the predictions of his theory of gravity was that anything with mass should bend light. So let's say you're the Earth, and I've a star, or say the sun right here, and there's another star behind. In sort of Newton's idea of gravity, light has no mass, so as it passes close to that star, the sun, it would just keep going in a straight line. But Einstein said no, the way he thought about gravity, what will happen actually is light, which has energy or mass, E equals mc squared, arguably the most famous equation in physics, right?
That no one understands.
That no one understands, but it's mass and energy are equivalent. That's sort of the idea, right? That as that ray of light from that distant star passes by the sun, it should get bent because it gets attracted to, the light ray gets attracted to the sun, so its light gets bent. And so if you have, light on this side, it would get bent. So basically that mass can act to focus light. So that came out in 1915. Well, in 1916, there was going to be a total solar eclipse. And if I don't know if you made the trek last summer to see the solar eclipse, would you go?
We were shooting to go to North Carolina
Yeah.
to see it, and the timing just did not work out.
Yeah.
But I had it planned for months. I had everything.
Yeah.
I was like, I need to see this full solar eclipse. Did
Yeah.
you see it?
I did.
Oh.
We drove out to Idaho.
Oh my!
So we were in the path of totality, and the further west you go, the better the weather was going to be, and the longer, and it was just mind-blowing and life-changing. It was incredible.
And that's exactly what I said prior to it. I was like, I want this to be life-changing.
Yeah. It really amazing. The next one is in the 2020s. It's cutting through continental U.S., going up through Buffalo, and so you got to make it out.
Yeah, I checked that out. I know where that one's going. You're right, Buffalo through St. Lawrence County, Montreal-ish area.
Right.
Yeah. Oh,
so
yeah.
pretty close to us.
Oh yeah. So I was like, okay, that's fine. I can
road
wait.
Trip.
I can wait.
That's right. Although the one I think next year, they happen about every 18 months. The next one, I think it's 2019, is cutting through the Galapagos Islands. Wow. So
how exceptional would that be to be in the Galapagos?
I know. I'm watching.
And just know what happened in the Galapagos. Darwin.
Incredible.
That's his territory.
That's
and you're
right.
watching Newton and Einstein. Okay. That's. Tell me more about that. Tell me more about seeing the eclipse.
Let me finish the story real quick.
Please.
Yeah, okay, good. So there was going to be this total solar eclipse, which means that the sun would be blocked out, which means you could see the stars behind the sun. So this astronomer, Sir Arthur Eddington, famous astronomer, organized an expedition to South Africa, which is to part of South Africa, very difficult to get to. And what he did is the experiment was to measure the positions of the stars behind the sun. Right? So stars are here, sun is here. And then if you measure the positions of the stars when the sun's not there, you can see how much the light has been bent. The stars will shift position as viewed on the Earth. And so they made the measurement, and the data perfectly matched the prediction from general relativity, which was a remarkable achievement.
There was a lot of high fives that day and hugs, I bet.
Yeah, I'm sure. But that's just one example. That was sort of the first test. We have now made, I don't know if it's dozens or hundreds but many, many tests of general relativity. And it's literally to the decimal point, to as many digits as we can measure. General relativity has passed with flying colors. But Einstein himself said, I can't remember the exact number, but it was something like, 100 successes are fine, but all it takes is one failure. So if there's one experiment where general relativity doesn't match, then that may point us to a deeper theory or something wrong with the theory.
And to your point about the word theory,
Yeah,
and how it's used in just common vernacular, is like, this is my theory about why that happened or that.
Right.
Like we just throw around that word like it doesn't
Yeah.
mean much. But scientific theory is like what you're getting at is it's very, very solid, and there's thousands of people out there trying to disprove things. We've been trying to disprove general relativity for over 100 years.
Yeah, that's right.
And to your point, it's up to this point, it works.
It seems to work. Yeah, absolutely. We know it's incomplete though, because there are things that it can't explain. Not that it should, but where we've been able to test it, it has done well. And just to bring this up, because we're talking about it, one of the things that really bothers me colloquially is this idea. We say, do you believe in something?
Ooh, I hate that.
And so and especially in this age we live in, it's okay to not to have alternative ideas, right? About I don't think the theory of gravity is the right thing, but you have to put forward another idea that explains everything that the old theory does and makes new predictions that the old theory didn't. And if your theory is better scientifically here, right, then we should keep testing that and perhaps move to that. So there are some things, saying I don't believe in, a round Earth, for example.
Flat Earth theory.
Maybe we shouldn't go there.
No, please, John.
know.
You can vent about anything that's irritating you.
I don't know. But evolution's another one. Do you believe in evolution?
Right.
So
the age of the Earth.
Right. Many other examples.
And you're right. That seems just such like an obvious elementary principle. Like, okay, you can say you don't believe that for whatever reason.
Yeah.
But what next?
Right.
Do you just stop thinking?
Right.
It's just like you can't live in a world of just dismissing.
Yeah.
Just dismiss. I don't want that. Like it. And you get it though. Like things are hard for people.
Yeah.
Like people don't get simple things. Like, hey, you smoke cigarettes, you're gonna get cancer and die. Like, do you get that? But the Earth is round.
Yeah.
We have
for example.
pictures.
Right.
Pictures and math.
Right.
Everything else is round.
Yeah. So that said, we're all people, right? So scientists are prone to mistake. Oh, climate change is another one, right? Like these are basic measurements that you can make, right? The interpretation of what do these data mean, that is where, you have to be objective and, but mistakes are made. Scientists are people too, and they're imperfect, and we try to be objective, but we're not robots, right? We're all part of humanity. But really basic measurements like the fact that the surface temperature of the Earth is increasing, and the fact that it's snowing outside, which is weather, doesn't mean that the climate isn't changing, because that's the long-term trend. And so these are some of the challenges. So, for example, I teach undergraduates that take an astronomy class for non-scientists, and for many of them, it's the only science class they'll take in college. That's a requirement, right? And so conveying a lot of these ideas, getting them to both question what they read, because you can't just accept, oh, this is a fact. Don't question it, because it's such an important part of science to question. But at the same time, when to understand when scientific consensus has been reached, it's not arbitrary, right? It's the result of a rigorous process. But always subject to be turned over, right? Like if you have a revolutionary idea. So it's really it's kind of a subtle concept. It's, we want people to educate themselves and understand what is accepted as sort of fact, but also understand that there's no such thing really as a fact, but you can't overturn facts without data. You can't just do it, by fiat. So I don't know if I've explained that well, but
maybe I'll piggyback on that.
Yeah, go.
By the way, that water is yours if you want it.
I get my water if it's caffeine. Or coffee. I don't know. It's not good.
So when you have a lot of these non-scientific students that come in and they have these questions and maybe there's some resistance, but they're coming in with a totally different, like, this is their only science class.
Right.
Have they ever? How often do they trigger something in your mind that's like, whoa, that's an insightful question coming from that perspective of a non-scientific person? Does it make you think more, like some of these questions, some of the resistance to just, I don't want to, what do you mean?
Yeah, absolutely. It's very important to be around different perspectives. And so someone who's a business major or creative arts major, or, like I said, everyone has something to contribute. Like, it isn't meant to be an elitist process, right? Like, science is for everyone. You can make your own little discoveries, do your own little experiments, test ideas for yourself. All that knowledge is out there. And so being around, that diversity of perspectives and ideas and backgrounds, like, that's critical. And diversity is kind of a loaded word nowadays, but it really is so important. Like, we think of diversity as being, skin color,
superficial stuff.
So, well, I guess what I'm trying to say is it's broader. Like, you could be just, a white male, but come from a very different background, right? You might think, politically, as a white male, as not being diverse, but like a first-generation college student who's going to a small school, right, and is around people who, maybe from a higher socioeconomic status or had many other opportunities that student may not have had. That's diversity, right? And so all of those, and like in my class, right, these kids come from they're adults, right, young adults. They all come from different backgrounds, different majors, all of that. And so the way I teach is to not say, the tablets, right, from above, like, here are the facts, thou shalt, learn these. But rather I try to do very project-based sort of learning activities and working with data and have them make plots. So, for example, the expansion of the universe, there's data you can take and they can discover that themselves and measure the age of the universe just from actually manipulating their own data or taking their own data and analyzing it, not manipulating it. But yeah. It's
you talking like that and talking about diversity and just broader idea, different perspectives. It makes me think of, the more I learn about Isaac Newton, just he was all of that in one. Like, he was a polymath, right? Like, astronomy, physics, that was just kind of one of his things. This guy was proficient at so many unrelated things. Like, he just had a diverse mind. Yeah. His whole perspective was just, he wasn't one-dimensional. And I think that's the problem maybe we run into as just culturally, as society. We become one-dimensional, and then someone like he was like, bring everyone else in. Have these artists, have these business majors come in here and talk with me. And because it makes all of us, it enriches all of us. But then someone like Isaac Newton, it's like, he didn't need enrichment from anyone else. Like, that guy was insane. He was brilliant. So brilliant.
And I think by his mid-20s, he had basically upended all of physics, and
as a part-time thing, like, he was a theologian and all this. Can't even get into that. When I think of somebody like him or Leonardo da Vinci, I'm like, who are you people? Like, where did you come from? Like, thank you for existing. Like, right. It just seems so unlikely those people could exist, especially back then when everybody died at 10.
Right. Well, right. There have truly been some revolutionary people in history, and you can point to them as being, I use the word threshold, like, things were chugging along, and then all of a sudden it is a major leap in how we think about things and how we interpret the phenomena around us, and Isaac Newton was one of them, certainly.
From your perspective, because it seems in my mind at least, and even just common knowledge, we jump around. If there's anybody that's just semi well versed in physics and just science, they know the name Isaac Newton, they know Einstein, and there's not much else in between. There's not too much Michael Faraday talk or since Einstein though. So who's the next? Like, 'cause we know Stephen Hawking would be one of the modern ones. Is he even the level of influence and insightfulness that Einstein was? As brilliant as Stephen Hawking was.
Yeah, I'm pretty sure I'm not qualified to make that assessment.
Neither am I. But I just wonder, like, we're still, because I feel like I may have heard Stephen Hawking say we need another Einstein. Like, he's kind of not even saying that he's not even that as brilliant as and revolutionary as that. So how long do we have to wait? Another 200 years for another one?
Possibly. I think it has just gotten harder. We understand. We think we understand the world, right? Like our current theories work very well. So I mentioned general relativity. The other main one, sort of that governs the subatomic world, is called quantum mechanics, and it's very mysterious and probabilistic. And who was it that said? It'll come to me, but he famously said, if you claim to understand quantum mechanics, you don't understand quantum mechanics. Feynman, I think it was Richard Feynman, Caltech professor. And so it's another idea or theory that has worked extraordinarily well. And in fact, if quantum mechanics wasn't the deeper theory for how small particles like electrons and protons operate, then the sun wouldn't shine. Your computers wouldn't work. Everything, it's what builds up, chemical elements and the material world around you. Even though we don't witness it, ourselves on this macroscopic scale, on this high scale. So one of the big mysteries, one of the big problems in physics, and I think Hawking was referring to this, is that right now there's no way to marry general relativity or ideas about gravity with quantum mechanics. They just don't connect in any obvious way. General relativity is based on really a geometrical theory. It's based on the curvature of space-time and things like that. Whereas quantum mechanics is these probabilistic ideas for how particles move and interact. So the last 50, 60, 70 years really has been trying to integrate those two theories so that we can, maybe there's a deeper theory, right? A unified theory. And then from that, you get everything you get from quantum mechanics and you get everything you get from general relativity. So for example, string theory, about which I know the extent that it's called string theory.
Good, I was going to ask that, because that's our best attempt, right?
It's one, but the ideas of string theory have been around for a long time, but there has not been a successful closed. Like in the end, quantum mechanics and general relativity, like the set of equations sort of governing them, you can really write down, and we understand fairly well. But there's no analog in string theory yet. And so it's either people will continue to pursue it, or I think there's a lot of fatigue in trying to unify those two.
That could be one of those, man, I've wasted 30 years doing this.
Very much so. Yeah, very much so. But I think that's what someone like Stephen Hawking was talking about, was that, we need that next Einstein who will give us that deeper theory.
And even if the string theory would be wrong, it's still progress to know if it's not, right? It would still be like, okay, someone else did that. We could move on. We don't have to go down that road, and we could wait for this person to unify. Now the easy way I break it down, of course, is general relativity is the very big, if I'm understanding right, the very big explanation on large scales, and then quantum is just the tiny stuff. We have no idea what it really looks like. We just kind of know how it behaves, right? It's about behavior, and then where do those things, how do they work together? Yeah. Is that essentially the question?
Yeah, I like that. I think that's right. Yeah.
So what is gravity?
Well, right. That's where we started. So there are two places where those two ideas should come together, gravity and quantum mechanics. The first is at the center of a black hole. So the very center of a black hole is called a singularity, and nothing in physics can explain what happens at the singularity. Like, we can explain what happens, just outside, right outside the singularity, but there's nothing you can write down that, I think I'm going to go through a wormhole and go up on the other side of the universe, or I'm going to get crushed to death, or, I don't know, I'm going to meet Matthew McConaughey and show up in my bedroom back in time. I don't know. So that's the first place. The second place is the creation of the universe. So the instant of time when the universe began. So we can infer, or we have ideas for what happened at a fraction of a fraction of a fraction of a second after the Big Bang, but at time equals 0, we have no theory. There's nothing in physics, and so, but we're pretty sure that quantum mechanics and general relativity have to come together. And when we explain how they come together, we might be able to turn back that clock to the beginning of the universe and at the center of a black hole. So it's a little mind-blowing, but
it's completely mind-blowing.
Yeah,
because it makes no sense, but
but
it does.
Yeah. Well, it's a what is this, right? Rumsfeld said these are known unknowns. So, right. So we can identify, certainly there are unknown unknowns, right? We don't even know what questions we should be asking, but that's kind of the fun part. But these are, we've identified these places and times in the universe. We have our theory that goes back to right before or right after, right outside. And so, but everything breaks down right at those places. So they're known unknowns.
And whenever I read or watch somebody or talk to somebody who knows what they're talking about, like yourself, I just like when we don't know how it started. I just picture, and of course it's not like in a religious way. I just picture something or someone just snapping their fingers and then it's there, like right, like because we don't know how that bang or time or space just started, right? Is that what you're saying? Or the center of a black hole, like. It's just there.
Yeah. No, we don't. I mean, there are some other ideas. I'm going to wander into areas I'm not as familiar with, but there's this concept of a multiverse that, this isn't the only universe, and that there are many universes. That's the multiverse. And so our Big Bang was just another universe basically popping off or spinning off of an existing universe. And so that moment of creation was whatever process governs that. Okay, now I'm going to make a new universe, and maybe the center of a black hole is the spawning of a new universe in some other set of dimensions that we can't observe. But the key thing, here's the key thing. I know, right? The critical thing is that these ideas. It's okay to be creative, and every day there's dozens of papers. People write papers and their ideas. And one of them might be the right one, right? But if they're not testable, if you can't say, okay, I'm going to build a rocket and go into space, measure the curvature, I'm going to, measure the temperature of the early universe, because if it's a Big Bang, if the universe started with a Big Bang, that means earlier on, the universe was much smaller, denser, hotter, so it should be hotter. I should be able to see that relic radiation, and indeed, we've done that. That was predicted in the 1930s and discovered in the 1960s.
Static, right?
The cosmic
That was
microwave background. Yeah,
Okay.
right. And that was led to the Nobel Prize. And that's sort of one way to kind of follow what ideas are being rewarded by their impact. The Nobel Prize in various fields. So physics is one of them. Astronomy doesn't have its own. So the last time a Nobel Prize was given for an astronomical discovery, it was in 2011 for the discovery of dark energy.
Okay.
Which we're not even there. But there's another one.
That's another very confusing, head hurting topic.
Yeah.
Now the idea of multiverses, does that concept or theory have anything to do with the expansion that you've talked about? That everything's just constantly creating and expanding, and that's why maybe our universe is this, and then another one pops up here because it's just in a constant state of expansion? Would another universe be just a manifestation of continuous expansion?
I'm not sure I totally follow. I can describe what we've been able to observe for our own universe, and it's important to a universe is everything by definition, right? So for example, when I'm asked, well, okay, we're expanding. What are we expanding into? Well, you can't really answer that because that would be outside of our universe, and so we can only talk about what's in our universe, and that's a bit of a cop-out. I know it, but for that, the analogy is like a balloon, right? So imagine you're living on the surface of a balloon. You're a little bug or something, right? So you can't go in the balloon and you can't go off the balloon. You're confined to the surface of the balloon, the way we're confined to some extent the surface of the Earth. But now blow that balloon up. So if I had a ruler and you and I were two ants on the balloon, and then the balloon expands, it's like, whoa, we're further apart now. Well, what did we expand into? Well, the expansion happened in a dimension that we can't access. The balloon got bigger, but we, from our perspective, we measured that, but we can't. There's no other dimension, third dimension that we could go into. So that's sort of the analogy for how the universe is expanding. We're literally making more stuff in between galaxies. So the space itself, there's more space itself as the universe expands.
Now, I told you several times that this stuff excites me. It's very profound, and it makes me very optimistic. But the one thing that I always think about that I'm like, it bums me out about physics and astrophysics and astronomy and our universe and life is it's the one thing. Okay. I read it long before you said it, but it has to do with expansion, and that there's going to be nothing at some point, right? Like, we're not going to be able to see stars anymore. Not us. Like, we live in the prime time to live, apparently, because we're here.
Right.
So, but somewhere, how far in the future, I don't know if you recall, but our galaxies are just moving so far away from each other. Everything's moving away.
Right.
We're not going to be able to see anything eventually.
Yeah. So maybe, right? So I mentioned dark energy, right? So the universe is expanding, and if you think about it, right, gravity is an attractive force. So gravity pulls things together, right? So if you jump up from a floor, you're going to fall back down because the mass of the Earth is pulling on your mass and pulling you back together. So for a long time, 60, 70 years, the game in astronomy was, as the universe is expanding, all the matter inside, all the stars and galaxies and gas and stuff should be pulling on everything else. So however fast the universe is expanding, it should be slowing down, right? Just like if you take your pen or something, you toss it up in the air. If you toss it really fast, it's moving fast, but then it's going to slow down, reach sort of the top, and then come back to you. If you throw it fast enough, then it'll keep going, right? If you throw it 22,000 miles an hour, it'll escape the pull of the Earth, right? But gravity is attractive. So what astronomers were trying to do is measure how much mass is there in the universe and how fast is the universe slowing down. So it's expanding and slowing down. And then, is there enough mass, galaxies and everything, to stop the expansion and have it start coming back together? So that would be like, your ball or pen stopping at the top and coming back together. So the universe recollapsing. So the idea was called the Big Crunch. This is circa sort of through even the 1990s, say. This is what everyone was working on. Some scientists were working on. Okay, now imagine there's not a lot of matter in the universe. Maybe there's, not enough, right? So it's expanding, and imagine it would just keep expanding forever, right? But always slowing down because all the stuff is just pulling on itself. So that would be like throwing an object and expanding. The object keeps flying off and then keeps going further and further and further away, but always slowing down because gravity works on all distances. Like we're pulling on things at the edge of the universe. So in 1998, 1999, observations of these special types of stars called supernovae, exploding stars, were being made, and we can get into why that is relevant, but they were, these astronomers were able to measure how fast the universe is expanding, trying to get at, is it slowing down or is it expanding? Is it going to expand forever? And what they discovered was that the universe is expanding faster. Like it's speeding up. And you're like, well, okay. Well, but gravity only slows down. So what is causing the universe to expand faster? So like an anti-gravity, right? Like something that's repelling or pushing. So we still don't know. And we call that thing dark energy, but really that's kind of a branding tactic. Sounds mysterious.
Oh, it sounds
dark.
so cool.
Yeah.
It sounds so cool. It's
great.
Using words that we understand to explain something we don't understand.
Yeah. So when you hear the term dark energy, you're like, oh, well, what's that? And the answer really is we have no idea. Meaning, there is literally nothing. There is no textbook you can go to. You look in dark energy, and all it will say is, well, we've measured that the universe is expanding faster. We don't know why, but the thing we attach a label to it, and we call it dark energy. And it turns out that whatever this form of energy is, or this force, or whatever, makes up 75% of the mass and energy in the universe today. So it's like, 3/4 of everything we know and love is actually made up of something we totally have no theoretical understanding of. So just to finish the story about how the universe will end, well, it kind of depends, right? Because the universe is expanding at an increasing rate today. Maybe it won't. Depending on what the force is, right? It might decide to turn off. It might decide to flip a sign, right? So we could expand forever and ever, or we could turn around and then start collapsing and accelerate, kind of crunch together at an increasing rate. So there are all these, there's the big rip where the universe will just, expand itself away. The big crunch, like these are just,
What would panic you more if tonight you went home, looked through your telescope, and you're like, oh no, galaxies are getting closer now. Everything's getting closer. Is this the crunch?
Yeah.
Like what time scale? If it started right now, if this is even the right way to phrase the question, if the expansion stopped and we started with the crunch,
right?
How much time we got?
Yeah. Well, I take comfort in the fact that things in astronomy work over very long time scales, so billions of years. So I probably wouldn't care. Right.
Well, what would you think?
I think I'd be more worried about an asteroid that we seem to have missed. That's like 2 days away.
Right.
But I saw that movie. Just send up Bruce Willis. We're good.
I just want it. Like I think it would be less mysterious if we were experiencing the crunch part right now. Mm-hmm. Like when Hubble look through his telescope. We're like, oh, everything's getting closer, right?
Right.
And everything's not running away from each other at a faster rate, like you said. I don't know. That would maybe make me feel more comfortable. We're like, oh, we got billions of years, and we know what's going on because everything's running away and we don't know where it's going.
Yeah.
Right? Like if things were coming closer, we're like, all right, at least we know where they're going. They're coming towards us.
That's maybe.
Maybe. That's just me.
We would still want to understand the why, and that comes back to your first question, right? Like, how did we get where we are today? What's going on now, what happened in the past, and what's going to happen in the future. And that's kind of the heart and soul of science. Where do we come from? Where are we going?
I spoke with my friend yesterday, and I did not confirm this at all, but he said that we're trying to reclass Pluto again as a planet. Are you aware of this? Or is this just some kind of silliness, internet silliness?
No. I did see something about that. Talk about a subject change, but I did see something about that, but I didn't dig into it.
Because I don't.
But
I told him, I was like, dude, I think it's probably just a bunch of Americans because that's the only planet Americans have ever discovered, right? Like it's like it's kind of a source of pride, and maybe. I think for people, I don't know. The astronomer who led the charge, so to speak, of Pluto being demoted from a planet to a dwarf planet. His name's Mike Brown. He's a professor at Caltech. His Twitter handle is very proudly Pluto Killer at Pluto Killer. And he's American. So I don't know. I don't think we should. It's not everybody, but I mean, here's the basic idea. Just with Pluto, it's fine. It's what's called a Kuiper Belt object. It's out in the outer solar system, and it was discovered in the 1930s, sort of serendipitously. But turns out there's thousands of Kuiper Belt objects, tens of thousands even. If you just think about what's the outer solar system like, well, it's cold. So there's lots of ice balls. They're basically snowballs. And so since then, we've discovered dozens of other planets or bodies, round objects, not just irregularly shaped rocks. At least one of which is actually bigger than Pluto, that are just out there in the outer solar system. So if you want Pluto a planet, you've got to bring in another 12 planets or so. Now you're up to 20-ish or more, because we may discover many more. So it's sort of, for my part, it's all exciting. We're discovering more about our solar system, but it's really like how the textbooks, slice up what we know. But that's what's so cool, is that what we know changes, and we shouldn't get attached to labels. But people do get excited, just like Pluto, like that's might be the extent of a lot of people's interest in astronomy. It's like,
for sure.
Oh, there's planet now. That's not a planet. Like,
right?
Why isn't that a planet?
Right. Well, but then if that leads them to why is it not a planet? Oh, wait a minute. There's a lot more that I didn't learn, when I was in school about what the solar system looks like, and.
These people are probably stupid scientists. They can't make up their stupid minds. They don't know what's out there.
That's right.
That's what people want to do.
That's something.
They don't know what they're doing. What are they fighting over? I do jump around a little bit, but what do you know about quantum fields?
Well, not too much. So. In what context?
What is a quantum field?
What is a quantum field? Yeah. So the physicists talk about. So we often talk about forces, right? Like a push or a pull, right? Like if I push on this, it's a force. But when you think about quantum mechanics, we don't actually think about forces. We think about fields. So a good analogy is the gravitational field. So the Earth has mass, and so there's a gravitational field everywhere around us. So you can think of it as something with a direction. So for gravity, it's down toward the sun or the Earth, and a length or a strength, right? So in other words, if you're right near the surface of the Earth, the gravitational field is strong. But if you go really high up in an airplane or up even in space, the gravitational field gets weaker because you're further away. So gravity, sort of the force of gravity of the gravitational field, gets weaker the further away you are, which makes sense, right? Like things should be close together for them to interact more strongly. So here's the question for you. Let's say we weren't here to feel that field. Would the field be here?
Does a bear poop in the woods?
There you go, right? So of course, it would be here. So a field is something intrinsic, something that exists from an object itself, right? And so then you come into the picture and you're like, oh, I'm in this field. Oh, and I'm being attacked. It's keeping me bolted to the earth, right? So fields are sort of a deeper way of thinking about how objects interact, meaning you think about an object in the field created by another object. And so you can think about like electromagnetic fields, you can think about magnetic fields themselves, gravitational fields. So quantum field is I'm not sure what context you're thinking about there, but it's a way of describing how subatomic particles interact with each other. So quantum mechanics, the probabilistic nature of quantum mechanics is sort of what those give you the equations of how things will move and where they will move and how. But we think about those interactions between particles in terms of these fields.
So all objects, something you said, all objects like gravitational fields, all objects with mass or all mass has gravity or what? So does that mean us too? Are you and I creating fields?
No, absolutely.
Like you and I have our own gravity. We're kind of pulling on each other right now.
And we are. Anything with mass has produces a gravitational field. Absolutely. Yep.
That's fascinating. That's complete everything.
Everything.
And
even a particle. I mean, a proton. You can think of it as producing a gravitational field around it. But the smaller the mass, the weaker the field, right? And so this is why. So if you think about it, why are planets and stars big? It's because gravity is a weak force, right? So it's a weak force because, try jumping up off the floor. No problem. You just defeated the gravitational field of the entire Earth, right? You haven't escaped it, but you broke it. And so planets and stars and galaxies are big because they're governed by gravity. And you need lots of mass in order for the gravitational field to be, to make a difference. People are small because we are held together by the electromagnetic force, right? It's like molecules and the bonds, atomic bonds between individual atoms and molecules that keep us together. And that's not gravity keeping them together, right? Like this cup doesn't have its structure because of gravity, it has its structure because of the chemistry, the molecules in them. And that's the electromagnetic field that governs them. And that's a lot stronger, many orders of magnitude stronger than gravity. And that's why you can make things that are small. That's one way to think about it.
That's a great way to think about it.
It's not mine. This was a TED Talk. It's a TED Talk called Big History. I can't remember the speaker. I don't know if you've ever seen it.
I know of Big History.
Yeah. So
actually, one of the guys I had on the podcast a few months ago was part of that. He's an AI researcher, RPI. He's part of the Big History, I believe.
Yeah, it's good. But it's a lot of what I've been talking about. Just a basic cursory understanding of the story of the universe, and how we fit into that story. But in that TED Talk, gravity. Big things are big because of gravity, and you and I are small because we're governed by electromagnetic force. Really cool, insightful.
There's something you said earlier about the Earth, and it's having its gravitational field, and it's pulling on it like something tiny, like you and I in this cup and everything. Everything, your glasses, everything's pulling on something. Yeah. It's just something you said earlier. I never really thought about it this way. The Earth, as tiny as the Earth is relative to everything around it, it's still pulling on the outer reaches of the universe, right? To a degree, it has some impact.
Yeah, there's no there's no limit on gravity. It just gets weaker and weaker. So it goes. It's like light. So if you shine a flashlight, into the night sky, you see it go away or get fainter, but that light, those photons, are still traveling, right? And they only get fainter because that light gets spread out over a larger and larger area. So in the same way, we are. You can think of it as emitting a gravitational field, saying, "Hey, here we are," and that field doesn't go away. It just gets weaker and weaker and weaker.
What is light?
Well, it's how we understand and observe much of the universe. So it's that's another loaded
it's everything.
Question. Yeah, well, kind of. It's certainly how we've viewed or made discoveries about the universe by things that shine. It's a light is actually very fascinating. It's a very unusual thing. So it's an electromagnetic wave. So if you take so light is an electric field that's changing. I know we haven't defined electric field, but turns out when you change an electric field, you get a magnetic field perpendicular to that. And so they sort of change. Oops, hold on, see if I can pull this off. They kind of change in tandem. And when you do that, when you have a changing electric field that produces a changing magnetic field that produces a changing electric field, that allows this thing that we call light to travel in a direction perpendicular to. So the electric field is this way, magnetic field is this way, and it'll travel in this direction, and it'll propagate itself. So it's called a self-propagating electromagnetic wave. So as opposed to imagine a still lake, and you toss a big rock or a pebble in that lake, right? You'll get a wave that'll propagate, it'll travel, that'll say, hey, I got disturbed, this part of the lake got disturbed, but eventually, it'll kind of die off, right? Whereas light keeps going. It allows itself to continue to travel. So it's sort of fundamentally, it's just energy. I don't know if that answered your question.
Well, when I ask questions, I never really look for the answer. You're answering all of my questions by triggering new thoughts.
Sure.
And so there's no, I started, where does it all come from?
Yeah.
I don't want an end answer. I just want,
for sure.
exactly what you're giving
me. So let me blow your mind then, right? Because what I just described is how we described light, or how we understand light circa 1865. So there was a famous physicist, James Clerk Maxwell, who took all these disparate observations. He's certainly in the sort of pantheon of geniuses, because he also did this in his mid-20s. So there were all these observations about magnetic fields and electric fields and current, electricity and wires and loops, and no one really understood it all. It was just all these experiments, right? And he took everything that had been observed and he synthesized it all into 4 equations that we call Maxwell's equations now. And one of the things that popped out of his equations was this thing that was a self-propagating electromagnetic wave that traveled at a fixed speed that we call the speed of light. 186,000 miles per second, right? And so those equations describe, what light is or how it's able to create itself and propagate, and he synthesized all of that. So that's light sort of as a wave. Turns out that light is also a particle. So you can also think about light not as a wave, like the wave on an ocean. You can think of it as what we call a photon, or like a bullet or a packet of energy. That, like when light strikes material, can think of it as like bombarding that material with those individual packets, and you don't describe it as a wave. So it was actually Einstein, there was this effect called the photoelectric effect, where when you shine light on a certain kind of material, it knocks out electrons, individual subatomic particles called electrons. And if you try to describe that process with a wave, with Maxwell's idea of what light is, it doesn't work. But if you describe it as a photon or a packet of energy, then it works perfectly. So light is both a wave and a particle, and we call that the wave-particle duality, that light can be one or both, or neither, or... So we actually don't really understand, sort of at a deep level, where that wave-particle duality comes from.
It's fascinating. God, that's fascinating that people figure that stuff out.
Yeah.
And are still figuring it out.
Yeah, so it gets worse, actually, because it turns out that it's not just light that's both a particle and a wave. It's actually everything. So matter is also, can behave both like a particle and a wave. So, for example, an electron I described, right, these negatively charged particles. You can do experiments where electrons behave like little balls of energy, just individual things, or you can think of them as behaving like waves of probability. And there are famous experiments that have led to Nobel Prizes that describe these phenomena. And the only way you can explain them is if both matter and light are either a particle or a wave, depending on the situation. And this is all in quantum mechanics, right? So quantum mechanics, I said before, we don't understand. Well, we really don't. Like, we don't know why. We just know that we have these sets of equations that tell us that things behave this way. We can go test them. Indeed, they do, but we don't have a deeper theory for where that comes from.
I'm going to let my brain just breathe for a second.
Yeah.
Just for a second.
Yeah, I'm core dumping about, I don't know.
But this
4 years of college and 6 years of... And I'm not a physicist, I'm an astronomer. So there are... you can certainly study, this is a lifetime of study, right? Like, you can delve into all of these areas much more deeply, and understand them at a deeper level. So I certainly don't claim to understand them at a deep level. And like for a lot of my work, I have to take all that work for granted, right? I can't tackle everything. No one can tackle everything. So I have my little slice of questions I'm interested in. But, there are other things like the expansion of the universe. And let's bring it back to the flat earthers, right? Have we ever been to space and seen the curvature of the earth? Well, no, unless you have, which would be very impressive. No. So we take that for granted, right? Like, there's a certain amount of common knowledge that we take for granted. And even though we haven't experienced that personally, I take it for granted that I have lungs and a heart, even though I haven't seen them. And so... in that same vein, right, just because I haven't personally observed something or personally made a measurement doesn't mean I can't accept it as sort of fact or canon. Maybe too loaded a word, but fact. So that's an important part of living, right? Because we can't do everything. We have to take that societal body of knowledge and use that to go off and make our own discoveries. And
you have to make assumptions at some point.
God's sake.
Or else you're never going to move forward.
Yeah. I mean, I think it's kind of interesting to try to rederive everything, but, that's It's kind of up to you.
No, let the alternate universe do
Yes.
all that. I like this universe, this planet.
Right.
The back to light.
Sure.
Because now I gave my brain a little break. Just like 10 seconds of like, okay, what was that? I'm gonna have to go back and listen to that. There's one of my favorite things to think about is like about light. And please, like, don't hesitate to tell me how crappy and wrong this is. But I believe the speed of light you mentioned earlier, 186,000 miles an hour, and so
Per second.
I'm sorry, per
Right.
second,
Faster.
Yeah, the thought experiment, I guess, is if you're standing on a platform and you're in outer space or just anywhere, and you're shining a beam of light in front of you, and right now the platform is stationary. You're just shining the beam of light. It's going 186,000 miles per second. Now, if that platform starts moving and you're still shining it, the idea would be just, okay, it's the speed of light plus the platform moving is the new speed of light.
Right.
But we've determined that that's not the case, and it's still consistently 186,000 miles per second.
Yeah.
What's that about?
Yeah. Well, so what you're describing is thought experiments that actually Einstein thought a lot about, and so this idea is that the speed of light is a constant. So whether you're stationary or you're moving, the speed of light is always the speed of light. It's just always one number. And that theory is called the special theory of relativity, which Einstein came up with, although it was very close. There were a lot of people who were thinking about the same ideas, but he really synthesized everything. This was in 1905, about 10 years before the general theory of relativity. And so before that, especially Isaac Newton and scientists through most of the 17 and 1800s, thought about this idea of an absolute reference frame, or absolute state of rest, or absolute time. So if you think about it, so what they thought about is that there was some kind of frame, some kind of place they could be in that was absolutely at rest. But there is no such frame. So in other words, we think we're at rest here, but actually we're, spinning around the Earth once every day, right? And the Earth itself is moving around the sun, and the sun is moving around the galaxy. The galaxy is moving through the cosmos. So there's no place in the universe that is at rest in an absolute sense. It's only relative to something. So we aren't moving relative to the surface of the Earth, right? But relative to the moon, we're flying, right? Or relative to the sun, we're whipping around, 30 kilometers per second. So a lot of the ideas of what we think about how the universe should work turns out are wrong. So we think we can be in an absolute frame of reference that's at rest. We think that, well, if I'm moving and I throw something, so like, if you're driving in a car and you throw something fast out the car, it's going to move the car speed plus the speed at which you threw it. It turns out that's not right for light. So even though it's counterintuitive, you can, again, design experiments that show that this special theory of relativity is right, and that the light is moving at the speed of light no matter what reference frame it's in.
That's awesome.
So, and just as an example, it's true. It has to be true, or it's the real world impact of it. Just to give you one example, is GPS satellites. So for example, one thing that it leads to, the special theory of relativity leads to, is that that time slows down when you're in a moving reference frame. So when an object is moving fast, and the faster it moves, the slower time ticks relative to a frame that is fixed or not moving, right? So in other words, if you go on a spaceship and you and I have a clock and we synchronize our clocks, you go off in a spaceship and come back. When you've come back, less time has ticked. So you've aged less than my clock at rest. So relative to one another, your clock moves slower. That's a phenomena called time dilation. So if you think about a GPS satellite moving up around the Earth, right, they're whipping around. So they're moving very fast. So if you didn't take into account time dilation, which comes from special theory of relativity, then we wouldn't be able to localize our phones wouldn't work, right? Like you want directions to the store or whatever, some town you're driving to, imagine it was off by tens of miles. You would not be very happy. But if the GPS satellites don't correct for that effect, the fact that their clocks are moving slower as they orbit around the Earth, then that's what would happen. Our GPS satellites wouldn't be good to a few yards; they'd be off by many miles.
Is that what's the difference? Like 3 or 4 seconds? That's popping in my mind.
No, I think it's a lot smaller.
It's a lot smaller. The GPS.
Smaller.
Did we know this prior to shooing them in outer?
Oh, absolutely.
So we're like, okay, we're gonna have to compensate for this.
Absolutely. Yeah.
That's so brilliant.
And any satellite company that hasn't done their physics aren't in business. I guarantee you. Absolutely. Yeah. They have to account for the change in how fast their clocks are moving compared to on Earth, which is where it matters if you're trying to figure out positions. You also have to account for the travel time, right? Like when that satellite communicates with the surface of the Earth, light isn't instantaneous. It's fast, but it's not instantaneous. So you've got to account for the distance that the light has to travel in order to coordinate where you are and where you want to be.
So it's the real world test.
Yeah,
right. It's
absolutely.
like, guys, this is real.
Yeah.
Your phone works. Your GPS works.
Yeah.
This is why.
Right. Yeah. It's quantum mechanics and your camera and all the electronics and network, communication, but also time and moving clocks, and it's all physics, man.
You should get a shirt. It's all physics, man, and have like a cell phone on it, a satellite.
You could do. That's good. Yeah, our physics club does always solicits ideas for like logos for like the physics club.
It's all physics, man.
That's right. That could be good.
Do you even physics, bro?
Yeah.
Do you have a favorite galaxy? Favorite planet?
So I'm gonna take the first part of that. So one thing I do that I encourage my students to, and I think, or I wish more scientists did, is just look at images of galaxies and look at their data. Like everything's big data, right? Like social media and GPS, right? Like Google, like Facebook, it's all collecting data, right? You can imagine like how much data just gets collected about the world around us and us every single day. So astronomy is not different in that sense. Like we collect enormous amounts of data. We are building new telescopes and new facilities to make more detailed observations, all of that. So we're very much in a world where we're awash in data. We always want more, but we're always trying to, that's how we do understand the world. We're doing more and more experiments. But you really have to step back. Like you have to take or at least I try to sort of step back and just not lose sight of that. I think that basic curiosity that I think for astronomy at least really attracts students to astronomy. We all look at the night sky. Who doesn't like looking through a telescope? Who doesn't like seeing amazing pictures from the Hubble? Well, I'm sure some people don't, but it inspires, right? It's inherently inspirational. You can think of it as like the oldest science, right? The first thing you can do is like wonder what's up there, what's out there. So anyway, So I try to do that. I try to look at just things that might inspire me. So looking at images of galaxies and just, oh my God, that is so complex. How are we ever going to understand that? Here's another one. Oh, that's totally different. Here's another totally different. So galaxies are as different as, people, really. But then the challenge is, well, what's common, right? Like, what are the common features? And by trying to figure out what the commonalities and the differences are, you can try to build a physical picture of where these things came from. So that's kind of how I approach it and how I try to inspire my students to think about.
You love it all.
I do. Yeah, it's good. Yeah.
It's this is something that happened last summer with a couple friends. One friend, I brought our telescope over to her house. She kind of lived in a field. And I was like, hey. She saw me unpack.
She lives in a field?
Well, her backyard's a field. Her backyard's a farm.
All right.
I'm sorry.
It's all good.
I was skipping ahead. I was like, that's irrelevant. Doesn't even matter. But
it's all good.
Yeah. You're right. I missed the detail there. She lives in a home
right.
behind the home field.
Right.
So you get a pretty good vista of the sky.
Yeah. Where was this?
This is Middle Pennsylvania.
Okay.
So it's fine. It's not like the middle of Idaho where you saw that,
Yeah.
It's not there, but it was still pretty good. So nice clear summer sky last year. I'm unpacking the telescope out of the car. She's like, what are you doing? I was like, we're going to look at Jupiter tonight.
That's awesome.
She's like, okay. I was like, you ever seen Jupiter? She's like, no. So I set up the telescope, found Jupiter, oriented at night. I was like, get over here. Check this out. She's like, what is that? Saw the Galilean moons going around it.
That's
right?
Awesome.
Galilean moons? Right?
Yeah.
Okay.
Yeah. Not moving, though. I mean, they were stationary.
Yes.
They move on timescales of days and weeks, but
they were there.
They were there.
And she's like, what are those?
Right.
Like, that's Jupiter's moons.
Mini solar system.
Right.
Yeah.
And seeing the color, seeing the stripes, seeing the orange and the white of Jupiter, she couldn't stop. She was so fascinated. She's like, what is this? She kept going back to it. Going back. And then later in the summer, camping in Vermont.
Yeah.
Another friend, I was like, hey, that's going to be Mercury over there. Or I'm sorry, not Mercury, Saturn. And you ever seen the rings of Saturn? He's like, no. I said, look in there. He's like, what is that?
Yeah.
Like, once again, same reaction. Just kept going back to it. Like, I can't believe what I'm seeing right now.
Yeah.
Like, that's real.
Yeah.
That's something. You
It's
talk about being inspired.
Yeah.
Yeah. So it's like, you can't get sick of this stuff. You should. It's in all of us.
No, absolutely.
One across the board.
Yeah.
Hopefully, there's going to be a few, like you said.
The curmudgeons.
There's some people that there are thoughtless people. There are uninterested.
Yeah.
And that's
they
fine.
Just haven't. Everyone's inspired by something, right? And so, it's easy to be inspired by this. I have found, and certainly kids. I think some adults might get jaded, but it's.
I think it's because the world is beating them down.
Yeah.
Right. Like as a little kid, I actually saw a commercial last night. For I don't remember what it was, but it was basically a kid was in her room looking at pictures of the stars or something in a book, and her dad's like, "Get in the car, we're going for a ride," and he brought her out and like showed her the galaxy, and I was like, "That's really awesome for little kids to experience that."
Yeah,
but we got to tell adults to do it too.
Yeah,
like
absolutely.
Why do we just like it's a game? Like it's like that's for little kids. Like that's a lot of a way I think people think about the universe and astronomy and the planets and the stars. It's like, no, it's not a game for little kids. It's not like just something flighty. It's real. There's nothing more real than looking through that telescope and seeing the rings of Saturn.
I think it gets, our world, right? We're stuck right here, right? Our day-to-day grind and our phones and like our stresses and traffic and all that stuff. And I think it's, especially for adults, it's critical to just step back. It's like meditation or relaxation, right? It's inspiration and curiosity kind of re-spark that there's a bigger universe out there. And looking at things yourself is a great way, an easy way to remind yourself of that, that childhood inquisitiveness. And actually, there's a great opportunity to mention that so Siena College is building a rooftop observatory. So is going to be the largest telescope in the Capital District, fourth largest in New York State. So how many inches? It's a 0.7 meter, so about 30 inches.
2.5 feet ish.
Yeah,
Ish.
yeah, 20.
Ish.
Yeah. So it should. Anyway, big by small telescope. Certainly much larger than any backyard telescope that you might get, which might be like an 8-inch or 6-inch telescope, right? So this will be 4 to 8 times bigger than that, depending what you have. So we will certainly be doing public observing, so public, events where you can come and look through the eyepiece. So we'll have an eyepiece, but we also will have a state-of-the-art camera and what's called a spectrograph, which is like a prism, allows you to split the light of an object in the way a rainbow gets split by raindrops in clouds, which allows you to make other kinds of measurements. But certainly the images of objects are going to be very inspiring. So construction actually began this month, and we should have first light sometime in September. So over the next year or so, look for
that is so exciting. I'm so excited right now.
Yeah,
I did not know this.
Okay,
wow.
Yeah, it was. We got this competitive grant, and it turns out that for about $250,000, you can get a state-of-the-art telescope, dome, camera, spectrograph, and it'll be robotically capable. So we'll be able to do remote observing.
Wow, that's fantastic.
So
and you have to is it Williams College or some other college that has a little observatory? It's like every Friday night during the summer, 8:00. It's open to the public.
Yeah.
Come check it out.
Yeah, so there are many great opportunities here because students will be trained. Our students, our physics students, will be trained and to operate, and so they'll be organizing. Faculty will be there to sort of help us get it off the launch pad, so to speak. But really, it's going to be student driven. It's also going to be a research telescope, so students who want to do their own research projects. It'll be for the students, the non-scientists who are taking introductory astronomy. They'll be able to do both eyepiece observing and take their own observations. And then, of course, for the broader public to, inspire people to be curious about the world and pursue science and ask questions.
You're going to be able to see Jupiter's red spot pretty well through that kind of telescope, right?
Yeah, it's going to be pretty impressive.
Wow.
Yeah.
Now, what's the word? The spectrometer?
Spectrograph.
Spectrograph. Is that something that you would? Is that like red shift, blue shift kind of?
Yeah. You'll be able to. So spectroscopy is a very important tool in science, but it basically you take light and you split it up into its individual pieces. So for example, this bottle is blue here because it's absorbing all the other wavelengths of light. All the greens and purples and reds are being absorbed by the molecules and atoms in the bottle, and the blue is being reflected. So there's light in this room, it's bouncing off, everything else is being absorbed, and the blue is being reflected and coming into your eye. So it looks blue. So light, it has different amounts of energy at different colors or wavelengths. And so when you split the light of an object, so like a distant star or a distant galaxy, you can figure out a lot about it. So for example, its composition. What is it made up of, right? So you could figure out through spectroscopy, what is this made up of so that it only reflects blue light. So you can figure out what is a star, the composition of a star, meaning how much of every element does it have. And you can also figure out how fast it's moving. So if it's coming toward you, then what happens is the light gets blue shifted. It gets shifted towards higher energy or shorter wavelength. If it's moving away from you, it gets red shifted or moves towards longer wavelength or lower energy. And this is how actually the discovery of the expansion of the universe was made. It was by taking spectra of galaxies, and it's like, whoa, they're all moving away. And the further away they are, the faster they're moving away. And that's what led to, this was Hubble's famous discovery, 1926. So spectroscopy is very important, and it's awesome that we're getting one.
It's the backbone, right? Like there's, like you said, there's
it's a
so
tool.
many pieces.
It's a way of collecting data.
Was that Newton or someone else that darkened the room, made the room as dark as he possibly could, and then had like a little pea hole of sunshine coming through, and then he shot that through a crystal or whatever it was, and then saw the wave, like the reflection, the light passing through that crystal, and then he saw the spectrum, the color spectrum, the rainbow.
Yeah, the rainbow. Yeah, Newton did do experiments like that.
That's crazy.
Yeah.
What was this guy thinking?
I don't know.
What are...
I'm glad he wasn't doing what he read in a book.
Right.
He was thinking.
Right.
That's what he was doing.
Right, man. Yeah. What do you do with it? How does a person like that function in society? What do we do with those people? How do we identify those people? I don't know. That's just especially back then. It was just like.
Well, he was very odd, and I'm not an expert on Newton, right? Because he was an alchemist and trying to make gold, and he was a shut-in.
Gold from lead? Was that one of his things?
Yeah.
But he was trying things. That was the thing. Even if you try things that sound outrageous, we know that they're not true because he tried it.
But I think that's why it's so important to not, I don't know if stereotype is the right word, but... Right, everyone. Science isn't owned by anyone. Right, we should not have a predisposition to viewing. Scientists has to be wearing a lab coat and working at some research. Like it could be in someone's basement, right? It could be someone from a very different background, and so science is open to everybody.
Ooh, can I try one of mine? And you could tell me how dumb it is.
Okay.
All right. And feel free to just be like, no, we figured out that's not the case whatsoever, because I have no idea. But this goes back to the special relativity that you mentioned, and when I talk about the platform and shooting light and its consistent speed. What if we're thinking about light differently? What if it has no speed? What if it's really just a tear in a field, and the photons are just tearing, like say you have a piece of paper here, and I just tear a piece of it off, and it's so hard to talk about this sort of thing, but say you're shining that light straight ahead, and it has a finite speed, I guess, but it's really not speed, it's just a tear in a field. See, I'm thinking in real time right now, which is tough, which is difficult. It's all good. But that's what I'm like. How can you explain that whole platform? And just like the sun is a source of light, galaxy source, and it's moving, right? It's moving the light, but the light is got consistent speed, so we don't add the speed of the moving object plus the speed of light, and maybe it's just the photons are creating a tear in some sort of field, and that's why it's just consistent. Once again, this is just to... Well, this is the first time I'm saying it out loud, so it's very clunky.
Yeah, no, I think it's fine to think, about different ideas and different ways of thinking about it, but let's kind of come back to this, right? Like, good to think outside of the box, but you also need to have a solid foundation on what we know or what we think we know, right? So maybe that idea works, but you've got to get... your next step, pick up a physics book, right? Start thinking about some basic experiments. You have your idea has to be testable, right? Whereas Maxwell's equations have been tested in detail, right? That those descriptions, those equations governing, how light works and propagates and it's a wave and a particle like that. There have been hundreds of experiments testing those ideas. So whatever you come up with, right, you need a
of course,
a test,
of
right?
course.
So yeah.
Yeah, I just needed to say
luck.
it out loud. Yeah. Good luck, non-physics dude. Figuring that one out.
No, it's good.
So back to astronomy and observation and telescopes. I've been so bummed out the past year or so every time they keep pushing back the James Webb launch. Like, so where are we up to, like 2020 now? I thought it was supposed to be 2018 a year or two ago.
Yeah. You and me both.
Dude.
So, yeah, right. So the James Webb Space Telescope is going to be phenomenal. So the Hubble Space Telescope, which has transformed astronomy, it's really been one of the main workhorses for exploring the universe and in fact, this discovery of dark energy, there were critical observations made by the Hubble. If we didn't have it, those discoveries would have been delayed. I mean, there's an innumerable number of things where the Hubble has been transformative. So the Hubble Space Telescope is a 2.5 meter mirror. So, and the whole thing is about the size of a tractor trailer. So take a tractor trailer, throw it up into space, put some super precise cameras on it. It orbits the Earth every 90 minutes or so, and you can observe the distant universe, and it's been phenomenal. It's been up there almost 30 years now. So the James Webb Space Telescope is going to be a 6.5 meter telescope mirror. So the whole thing is about the size of a jumbo jet, like a 747 jumbo jet. And so I think you can picture that in your mind, but like you should actually find a picture and to scale of like what a 747 and a big rig, like big rig's big, 747 is gigantic. So now take this thing, and we're not putting it so that it orbits the Earth. We're putting it in an orbit around the sun at a place past the moon. So it's one of these special places. It's called one of the Lagrangian points. And why would you do that? Well, the reason is the sky is very dark. So you think space must be dark, but because the Hubble is orbiting the Earth, there's a big part of the sky that the Hubble can't observe because the Earth is in the way, right? So, and so the James Webb Space Telescope is going to be further out and sort of a bit better part of the solar system in terms of being able to make really sensitive observations. And it's going to be, almost triple the mirror that the Hubble has now. And, why do you need a bigger mirror? So you think of astronomers are very greedy with photons, right? We want to collect as much light. So I think of like mirrors as being like light buckets, right? So imagine, light was streaming down from the sky and you had a little bucket, you might collect a few photons. If I had a bigger bucket and I can leave my bucket outside longer, I'm going to collect more and more light, right? So bigger mirror, bigger light bucket. So we can see fainter objects, more distant objects, and really, look for Earth-sized planets around other stars and look for the first stars and galaxies that formed in the history of the universe and peer through the nebulae that are the birthplaces of new stars. It will truly be transformative in terms of data, in terms of information. But as you said, it's been delayed, and it has not only been delayed, but it has cost far more than was originally intended. So yeah, I the new launch date, I don't have the date. I know it's 2019 at one point. It's probably going to be pushed back beyond that. It was supposed to launch. I think 2018 was the original launch date for a long time. It's cost something like 10 times what it was originally supposed to cost. So I think it was going to be $1 or $2 billion. It's now well over $8 billion. Now with the delays, probably a lot more than that. The reason is it's new technology. And so it's to be able to make this super amazing telescope, you don't go to the hardware store and I don't know who goes to the hardware store, but you don't go to Home Depot and get yourself a telescope. Like, it's a lot of new technology and therefore really risky. So, for example, the telescope is so big, it doesn't fit in any of our rockets. So, right, you've got to launch it into space, you got to escape the gravitational pull of the Earth. And I said this number earlier, the speed you have to get something up to is 22,000 miles an hour, which is pretty fast, right? So that's why, hopefully you've seen rocket launches, right? Like, they're very explosive affairs, right? Like, you've got to, really reach a high speed. And so what the James Webb has to do is it's actually going to be folded and then put in a rocket, one of the biggest rockets that is available, that has been ever manufactured, launched into space. The rocket comes apart because most of it's fuel anyway, and gets out into this orbit past the orbit of the moon. And then the mirror is going to unfold like the petals of a flower in order to be this 6.5 meter telescope. And the amazing is not the word, but if it doesn't work, if anything fails in that very long chain of basically doing this precision placement of this super, precise machine, there's no way to repair it. We're done. Whereas the Hubble, I don't know if you remember, but there were servicing missions before our fleet of space shuttles were retired. I think the last one, probably early 2000s, right? It was, I think, the 4th servicing mission, because they installed a whole new set of cameras. But it was literally astronauts going up into space, matching the orbit with the Hubble, coming out, grabbing onto the Hubble, taking out the old instruments, putting in new tech, and then letting it go, and then astronauts come back to Earth, right? So
that's absurd.
Which is also absurd. It's crazy, right? But it's how we've been able to. It's how the Hubble has stayed relevant. And in fact, I don't know if you remember this, but it launched, I think, back in like 1992, 1993, but it didn't work at first. It was out of focus. So the first images from the Hubble were like, opening your eyes underwater.
Oh, that's right. I forgot about that. I do remember
or like
that now.
taking my contacts out.
Everybody was crapping on it.
It was a PR nightmare. This was before my my time as an astronomer. But so the first servicing mission was to they understood it. I don't recall the exact defect, but basically, the light wasn't being focused to a point. So you didn't make a sharp image, you made a blurry image, right? And so that was the first servicing mission. They fixed it, and now, now that's sort of lost lore in the Hubble's first few years, but it was a disaster. If anything like that happens with the James Webb, there's no way to fix it. We're hosed.
Scary.
Yeah, it really is scary.
Because it's not just it's humanity. Like, that's gonna help. Who knows what it's gonna discover?
Yeah, it'll definitely be transformative. I actually have a contrarian perspective because it has been so expensive. So as we have a limited amount of money. So there's NASA or astronomy, right, has a certain budget, right? Just like, you have a budget, I have a budget, right? And so we can't spend arbitrary amounts. You could, but then, can't buy groceries or fix your car or whatever. And so because it has been so expensive and has been delayed so much, it's actually taking resources from other. So, for example, scientists like myself, I apply competitively for funding from places like NASA, National Science Foundation, to do science. And that pot of money has been shrinking because it's been going to... So the James Webb is so big, it's actually a line in the federal budget. So, like, there is a row that is James Webb's budget. So it's basically, in some sense, sucking all the oxygen in the room and drying up funding for other activities. So you have to decide, as a public, we have to decide what's more important. Do we keep, throwing money in this hole?
Yes.
Because they'll burn through it. Do you?
I think the problem isn't money. I think the people that are in charge of allocating all of our resources are the problem. Put me in charge.
Maybe.
I'll tell you where we could take money away and put it towards that. Like the value is going to be, we don't even know. You say transformative a couple times.
I think that's right.
We don't even know how valuable this thing could be.
Yeah.
So we owe it to the people that have come before us, right? Before I didn't do anything, but it just existed that figured all this crap out. Your Galileos, your Copernicus, everyone. And we have to put the hard work in too. Yeah. Like, so what? We have to spend money. Like, we have the brain power. We have the resources to do it. We just have to allocate them properly because we owe it to those people who came before us as well as the future generations. Like, hey, we figured this stuff out. You guys got some new stuff to work with now. So put me in charge, man.
Yeah. No, I think that's a compelling argument. Someone else might say, well, we don't need this thing. We could do 3 of these things and they'll be equally transformative, right? That's where it gets hard. Like, why the James Webb? Why not, some other approach that would spend the same amount of money or maybe less, maybe a lot less, be less risky, but also be transformative in perhaps different ways. That's where it gets harder, right? But I agree. It certainly has. There has been, some degree, not to some degree, there has been mismanagement.
For sure. The thing that irritates me is the LHC. Why is it in Switzerland? They were building that thing. Switzerland, right?
It crosses several
borders.
Yeah.
Yeah. But they were starting, I guess, mid 90s, late 90s, that one in Texas.
Yeah, super collider.
Yeah, and then there's a bunch of dorks in Congress are like, nope, I don't understand it, forget it. And they're making incredible discoveries at the Large Hadron Collider.
Yeah.
And it's like, well, where's what do we do? I mean, we have we're not. I don't think we participate at all in the LHC funding over there, do we? I mean, we have scientists, I think, that are kind of there.
Yeah.
But I don't know how much we actually contributed. It makes me mad. I'm like, let's do something, United States. We're supposed to be the best at everything. Like, we're supposed to be the tip of the spear. So I don't care about your funding argument, John. We're going to change this. I'm on the still sticking with the James Webb.
Sure.
Because you describe it like opening like a flower.
Yeah.
That thing is beautiful. That is a beautiful piece of
renderings of it are.
I have the good fortune of having a friend that works at NASA down in Virginia.
Yeah.
And he has access to the Webb, and him and his wife went there, and she took a picture standing next to the big gold plate.
Like in one of the clean rooms.
Yeah, she's standing right. I'm like, whoa.
Yeah. No, it really is phenomenal. The technology is remarkable. And in fact, I was working on 2 proposals to use the James Webb Space Telescope. And the deadline was, I can't recall, sometime in February. And it was a week away. And I'm like, I'm in the middle of teaching. How am I going to pull this off, right? And this is always crunch time. And then here comes an email. It's been delayed. New deadline is sometime next year. And I was like, well, don't have to work on this anymore. So I'll do it next year. So.
Is that were you jostling for telescope time? Yeah. Like everyone, what's that queue like? Is it?
Well, especially with a new facility, a new instrument, like the James Webb Space Telescope, it's going to be very competitive. Roughly, so the way this works is you basically make a case for your science. You say, this is the question, or these are the questions I want to answer. In order to answer them, based on what we already know, I need these observations. So you really need to understand its capabilities. You need to understand what it can do, what it can't do. You might use one instrument for a certain observation, another instrument all on the James Webb for another instrument, and so there is what's called a telescope allocation committee, or a committee of peers, all anonymous. So you don't know who's on that committee. and they take all these proposals and they read them and they rank them, right? So if you make a really and I think there's an interesting point you may not be aware of. Anyone can get time on any of these telescopes. These are public. They were built and they're being operated like the Hubble with public funding. So if you sat down and you wrote a compelling proposal, you don't need to be, at a Harvard or a Caltech or a Berkeley or, even a Siena, because I get telescope time on the Hubble. It can be your home address, and if your science is compelling and you can demonstrate that you can do that science, if you were to get the data, then you can get time and funding, actually.
John, we might make a good team.
Yeah.
I can be persuasive. I can write very persuasively.
All right.
And you...
Give me money.
You know stuff.
Well,
like, we could work on this together. That'd be so exciting. All right. Well, we have a few years to wait, probably. So all right.
You gotta learn all of
let's
physics,
play this. Right? Yeah, or maybe I just want to look at cool stuff.
Yeah.
You could do the physics parts. I'll just have a bunch of silly
I'm
questions.
the short end of the deal here.
So, all right. So let's play some more fun thought experiment games.
Yep.
My buddy Esther is like, talk about aliens or something. I was like, we'll see. So say with the James Webb, say if we do discover a second Earth, right?
Sure.
What do we do with that information?
Well, there's always questions you can answer or ask. So one of the big threads in science, astronomy, is the life in the universe question, right? So right now, the Earth is the only place in the universe that we know of that where there is life, intelligent or otherwise, right? Even primordial. So we're trying to understand: is this a unique phenomenon to the Earth? I think most scientists would say no. I think largely because that would be pretty arrogant, right? It's sort of the we've made this mistake before, right? When we thought we were the center of the universe and everything orbited the Earth, and that we were really special.
We kill people for saying that. Thing that was right.
Yeah,
we kill people.
Yeah.
Because they were right.
That's true. So it's unlikely that we are the only place in the universe where life arose, but we still don't have evidence of life anywhere else. So, for example, one of the core missions of all the or goals of all the missions to Mars is to look for evidence of past life. We don't think life exists there now, but is there evidence that there may have been life in the past? Even that question is very important. So a lot of astronomy is focused on life in the universe. Well, where do we think life arose? Well, it arose on an Earth-like planet, so let's look for Earth-like planets, right? So there is the question of finding Earth-like planets. And what do I mean by that? What I mean is something with a solid surface, right? So Jupiter in our solar system is the biggest planet, but if it has a solid surface, it's sort of this core under the very dense pressure and of the weight of the atmosphere above it, right? It essentially has no solid surface. So we don't think that's a good environment for life to arise. So we're looking for Earth-like planets that are perhaps in what's called the Goldilocks zone, or the habitable zone, right? So not too close to its parent star, because there, you've got the intensity of the star, and it's too hot, life might not be able to arise, and not too far, because if it's too far, it's too cold. Something like out in Pluto and beyond, there's not enough energy. So if you're just the right distance, where water in particular can be in its liquid form, perhaps those are the right ingredients for life. I keep saying perhaps because, again, it's we have no idea, right? We've found life in and around these volcanic hydrothermal vents at the bottom of the ocean, a mile deep, and that's like nothing, right? So you can imagine some distant moon that's super far from its star. That is where you have life in its interior. So it's very important as we pursue evidence of life in the universe that we don't get too comfortable in what we think it should look like. But anyway, you got to start somewhere. So discovering Earth-like planets is an important part of it. The James Webb is going to be imperative for that. But we have a number of candidates even now with today's technology. The next is, does it have an atmosphere, right? Like, something like Mercury with no atmosphere. Well, we think life needs something to breathe. It doesn't have to be oxygen, right? But so an atmosphere we think is as an important part of that. And then once you've discovered that, well, is there evidence of photosynthesis, right? So if plant life is in some sense, a more primitive form of life, a basic thing that might arise in the right conditions. So you can look for evidence of photosynthesis or water in the spectrum of an atmosphere. So there's like these deeper and deeper layers, right? So short of actually traveling to these planets, you can ask deeper questions of, is there evidence of life in these places? And obviously communication is another one, so see where that goes.
It's because in a very real way, this is still we're such in the nascent stages of discovering.
Yeah.
Like, what is all this? This is like Christopher Columbus.
Yeah, very much
like
so.
What? I don't know what's out there, but I'm gonna go look.
Yeah.
And the technology is becoming phenomenal, and the brains that it's attracting it's
exciting times because astronomy is unique in a couple ways. First, I tell my students this a lot too. We can't go out and grab things, bring them back to the lab and like poke them and prod them and burn them and all of that. So like everything we think we know about the universe, stars and planets and distant objects, we have to observe from our place, stuck here on Earth. And so we have to be innovative about how we make those observations. So that's one thing, right? As opposed to like engineering, right? Like you can build something, break it down, build it different, or chemistry, right? You can test different reactions, how elements come together. So that's one thing. The other thing is, it's a very dynamic science. We've talked about like some really big picture ideas about the universe and all of that, but there's also just a lot of just technology, right? Like we're building sensitive cameras, we're building, rockets and satellites and, new instruments that are trying to make really sensitive observations. We're trying to find things like Earth, like basically the edge of the galaxy. And that's really hard to do because they're really small and these things are very far away. There's a lot of empty space. So you get to, as an astronomer, you get to work with, people that work on the technology and the engineering and the, installation of things, and, rockets and satellites, but also the science and how do you ask these questions? How do you analyze things? How do you make sure you're not fooled? How do you, adapt and change your ideas from what came before you and fit in your new observations with, it's a wonderful marriage. It's like innovation and curiosity at like the bleeding edge. And that's really what drove me to astronomy, or inspired me to be an astronomer.
Do you want to wrap this up?
Yeah.
Because I will keep you for another 10 hours.
Yeah.
All right. This has been great, John. This is fascinating. John Moustakas.
Thanks for a great conversation.
Siena College. Wow, you guys are getting a telescope.
We are.
I'm gonna queue up. I'm gonna write you a proposal after this and be like, I should be the first one in the public to use this. I'll write.
Yeah, get in line. No, it's gonna be fantastic, and we will certainly advertise it widely. for members of the community, and it's going to be a great opportunity to pique your curiosity and keep you asking questions.
And I will tell everyone I know about it because
Excellent.
it's endlessly fascinating. Thanks again, John.
All right.
John Moustakas, Siena College.
All right.
Bye. Thanks, bud. Woo! I love some of that stuff, man. Woo!
How long was that?
That was...